Sanjay. Yeah, Kumar.
Yes, sir. Yes, sir.
Your voice is not clear.
Voice is not clear.
Yeah. Right now, little bit. Can you please loudly? Can you say?
Okay, sir. Okay. When I start the session, I'll be more louder than this. I'll try to be
Okay.
more louder.
So I suppose can we start this session?
Yeah, sure, sir. We'll start.
Okay. So you can share this screen. Then we can please start.
Can you please come again? I couldn't hear you properly. Yeah, shall we start?
Yes, sir. So I will just say here that the Kumar, yeah, that Kumar sir is working in this IoT and he is the technical in charge in that and he is to solve the technical issue and he accepted the invitation and he is agreed to deliver your lecture and so it is a good thing that you are able to explain to us that what is basically whatever the things we have learned now till yesterday very long now we can learn about the FPGA. Okay, so yes, so now I hand over to Kumar.
Okay,
So
okay, sir.
you will please start. Thank you.
Yeah, is my screen visible?
Yes.
Okay, sir. So yeah, this is Kumar from Coreel Technologies, and I'm the application engineer there. So we basically deal in AMD Xilinx and Siemens EDA portfolio. So if you have also heard about Sandeepni, who is the authorized training partner for AMD Xilinx in India. So basically, we are working with Sandeepni. Like Sandeepni is a sister company. So like if anybody is interested to go for any internship programs or if you want to learn more about FPGAs and everything, so you can anytime opt for Sandeepni programs, which are based like available on chargeable basis. Okay. So just this is about the information for the students. So we'll start with the session. So today's like agenda for today, as we have discussed, it will be like around. We'll be talking about the FPGA architecture, like what are the advancements there in the 7 series architecture, what are the resources available, and how we can utilize them. And also we'll have a we'll be able to virtually look at the architecture of the FPGA and while we do the practical sessions also. So talking about the practicals, we'll discuss about a small example on VIO. So we'll see how we can design a counter using IPI, Vivado IPI. Okay. Yeah. So let's start about the 7 series FPGA. So if we talk about the 7 series FPGA, so these things that you can see here, like the logic resources or the memory multipliers, programmable interconnects, input output bands, global clock buffers, boundary scan. So these things are like common to all series of FPGA. So what advancements we have seen in the latest 7 series is, so if we talk about slices, so slices are basically of two types. One is your slice L and other one will be your slice M. So slice when M, we can also call it as full slice. So in slice M, what exactly happens is the LUTs that we have there in the slice M, that can be used as your memory or either as your logic. Okay. And apart from that, it also contains your multiplexers and carry chain logic. Okay. So These are also basically used to implement your RAMs, or if you're trying to implement your SRLs. Okay? So anything related to memories, that you'll be able to implement using the slice L. The next thing is we have slice L. Uh, Slice L is also called the logic slice. So this the LUTs that we'll be having, that will be used for your logic and not for the memory. And apart from that, it will also have your muxes and carry chain logic. Okay. And other resources, if you see, we have interconnect resources which are used to connect all your like these are like switching routers, which are used to connect all your logic blocks, your configurable logic blocks. Okay. And we have input output bands, which will be there for your having an interface with your external world, like from the FPGA fabric to external world, or like if you're sending some signals from your external world to the FPGA fabric. And if you talk about the other resources, we have global clock buffers. So this will be your clock buff G buffers will be there. That will help to distribute your clock throughout the circuit. And we'll also have a boundary scan logic that you'll be using for your debugging purpose, for your boundary scan testing. So these slices and all that we talked about. So as we discussed, these slices will have LUTs, right? So if we talk about the earlier series of FPGA, you could see there used to be a two-input LUT. Then later inventions you used to have four-unit LUTs. So now there will be six input LUTs that will be available in the slices, and this six input LUT will be four in number. So total there will be four LUTs in one slice. That is either it is slice M or slice L. There will be four LUTs, and these LUTs, as you all know, that these LUTs are used to implement your combinational logics, right? And when we talk about the flip flops, so as we discussed, this slices will have your LUTs, it will have your flip flops, your carry chain logic. So in each slice, there will be eight flip flops that will be available. So flip flops, as we know, it is used to implement your sequential logic, or it can be used as your storage element, which can store about one bit of data. So if we talk about the flip flops and latches that are available, so there will be four of the flip flops that will be used for as your like, will be used as a flip flop, or your you can say it as can be used as your storage elements. And other four latches of flip flops that are available that can be either configured as your flip flops or either as your latches. Okay. Apart from that, we'll also have multiplexers inside our FPGA logic. So if you have heard about the earlier series, if you talk about the 3 series FPGA, so there we used to have F2 and F3 muxes, right? So now in the F7 7 series FPGA, we'll see there will be F7 and F8 muxes will be there. Okay. So these how these multiplexes are implemented. So using the LUTs itself, you'll be able to implement the multiplexers. So let's say as we discussed, we have a six input LUTs. So the six input LUT, you can use the six input LUTs as a 4 cross 1 mux, right? So 4 cross 1 mux, 4 will be your input, and the two other input lines that we have, that will be used as your select lines. Okay. And these LUTs, multiple LUTs, we can combine together and we can come out with a F7 or F8 muxes, right? So all of these things that we are talking about, that is your LUT, there is a multiplexer. So all of these will be implemented in the FPGA fabric when we come to the practical part. Okay. So also we discussed about the carry chain logic that will be available in your flip flops. So these will be implemented using the multiplexers and XOR gates. So generally these are used for your arithmetic operations, like you say additions, multiplication, subtraction, those applications it will be used for. And apart from that, there will be clock buffers and there will be some clock manager tile as well. So we'll discuss about that in the later slides. So talking about the 7 series FPGA families, so here you'll be able to see from Xilinx we have Spartan 7, Arctic 7, Kintex 7 and Vertex 7 FPGA. So these are the four uh, boards which are part of the 7 series family. So these boards will have like multiple editions will be there for these boards, which will have uh, different features, which will have different number of pin input output pin counts. Okay? And apart from that, there will be like ultra scale and ultra scale plus variants to all of these boards. Okay, so these ultra scale and ultra scale plus variants, like this works on based on the nanometer technology. So if you talk about the simple FPGA series boards like Spartan 7 or Arctic 7, Kintex 7, so these boards are all based on 28 nanometer FinFET technology. But if we talk about the ultra scale boards, that will be based on your 20 nanometer technology, and ultra scale plus will be based upon your 16 nanometer technology. Okay. So as we were discussing about the logic cells in the earlier slides, so this logic cells will consist of your CLBs and inside the CLBs whatever we have. So these will be, you can see if you talk about the Spartan 7 FPGA. So this one is the industry's lowest cost and lowest performance FPGA that we have. And as we go up the architecture till the Vertex 7 board, so you'll be able to see this is the highest performance and highest cost board in the industry right now. So as we go up the architecture, we'll be able to see there will be increasing number of logic resources. So number of CLBs that you have, the number of LUTs or your flip-flops that you're having inside, those all will be increasing as you go up the architecture. So similarly, if you talk about the block RAMs, so block RAM capacity will also increase. DSP slices, yeah. So apart from this logic resources that we have, we talked about, that is your slices, inside the slices that we have multiplexers, flip-flops, LUTs. So we'll also be having some block RAMs and DSP slices as well. So these block RAMs, we could be able to store your data into to read and write data across the block RAMs. And we also have DSP slices. So these DSP slices are used to implement like arithmetic operations. So which are commonly found in your digital signal processing applications. So, for example, if you say it can be used for implementing your FIRs or IR filters, or if you talk about your FFTs, IFFTs, image and video processing applications. Okay. So, similarly, if we see for the Vertex 7 FPGA, so this will have the highest performance of the DSPs. That will be 565 Gmax per second. Okay. So, apart from this, we hello. Yeah. So apart from this, if you also talk about the microblaze CPUs, so there will be a software processor that will be there inside your FPGA fabric itself, which you can infer from the FPGA IP integrators. So these microblazes CPU that you have, these are like software processors and not any embedded system on chip that is there on your board. So these are like software processor which can be implemented as a microcontroller. So if you want to implement it as an RTOS, like a real-time operating system, so those kind of applications can be done using your microblaze CPUs. Okay. Apart from that, if you talk about your transceiver speed, serial bandwidth, PCI interfaces are there, memory interfaces will be there, IO pins, voltage. So all of these will be increasing as we go up the architecture of the FPGA family. Correct. So we'll just see a virtual representation of like if we are going to implement some design, how those designs will be get implemented on a FPGA fabric. Right? Yeah. So this, what you can see on the screen currently is, this is the virtual representation of a design that has been implemented on the FPGA fabric. So this part which you can see here, the blue color dotted things that is accumulated at the corner of this uh, FPGA is like these are your implemented design. So these are the resources that are being utilized. Okay. So this if you can see, this is like the complete. It will be consisting of your CLBs. There will be routing resources in between. On the sides, there are like your input output bands. That is your IOBs will be there, right? And these blue color lines which you can see, so there will be squares of there will be kind of a square column, and where your all your CLVs will be placed, and those CLBs only will be occupied when you are implementing any design on the FPGA fabric. On the left hand side, you can see this is my processor. So if you are using any Zinc processor for your system, so you'll be able to see like this will also turn blue in color. Like this can also be used your processor part. So this part which you can see the which you can see which is having your CLBs on everything. So this is my FPGA fabric. This part, and on the other side, this part is my PS part, my processing system part. Okay, so we'll see about the same thing like how this processing system and FPGA fabric work together in a coordination when we have a Zinc series boards. Okay, yeah. If you see this, this is a virtual representation of my CLBs of my slices. So here you can see this is my slice L and this is my slice M. So both of these slices belong to your Y37 block, Y37 CLB. So my CLB number is Y37 and these slices are this X37 and X36 are my two slices. That is my slice L and my slice M, right? So let me see it. Okay. So if you can see on the left hand side for your slice M and slice M will have the same logic resources like the same 7 muxes and your same slice L also will be having the same resources. But slice M if you are using this will be can this can also be used to implement your memories, your RAMs. But this slice L that we're talking about okay. So on the left hand side, these things that you can see, these are my LUTs. These four LUTs will be there. So as we discussed, in each of the slice, there will be four number of LUTs. So these are my four LUTs. These are my F7 and F8 muxes there. Okay. And in the middle, you can see this is my carry chain logic. So here also we'll be having some multiplexes and a XOR gate to have a look at carry logic. Okay. And on the right hand side, as we discussed, in each of the slices, we are going to have eight number of flip flops. So these are the eight flip flops. These four flip flops. Similar fashion on the slide side also will have more details. So earlier, if you see, we discussed about the only the programmable logic. So this are your that specific board in the there are based on the so the programmable logic how does it work?
Sir, you are not audible.
Sorry. Hello. can someone please confirm if I'm audible?
Yes, sir.
Okay, okay. Yeah. So we're talking about the Zinc 7000 series architecture. So if we talk about this, so here this works on the basis of your AMBA protocols. So what exactly we're trying to achieve here is when we're working on some Zinc series, so we try to communicate with my programmable logic, my FPGA fabric through my processing system for some hardware acceleration applications. Right. So here we use the performance of my uh, SOCs, that is my system on chip, plus my the we use the FPGA fabric for my designs, right? So when we are doing that, so we use number protocols for my connections between my processing system and my programmable logic. So for that, we are using the advanced extensible interface. Right? So this advanced extensible interface is it is a widely used protocol for connecting your IP cores or module within the FPGA. Right? So this basically defines the like set of instructions or rules for your high performance communication in your different components of your FPGA. Okay. So if you see here, there will be four high performance ports, and these are marked as your slave ports. S means your slave ports. So this will be your slave AXI high performance 0, 1, 2, and 3 high performance ports. And one other port is your slave AXI ACP port, that is stands for your accelerated coherency port. So this basically is used for your accelerator applications where you're going for some video applications or video processing applications. Okay. And apart from that, you'll also be able to see the PCI will be there. So it will use for high speed data communication between your Zinc and the external peripherals. And there will be some slave AXI GP0 and master AXI GP0 ports. So these slave AXI GP0 and master AXI GP0 if I talk about, so these are like for your GPIOs. So I'll be having multiple GPIOs on my boards. So GPIOs will have could be your switches, your buttons, your PMODs. If you have uh, your Raspberry Pi or your Arduino, whichever there's whatever components are there on your boards which have pin connections. So that will be can your GPIOs. So those can be programmed as either your slave ports or either as your master ports. So that means either you'll be able to use my programmable logic or your FPGA fabric as your master and your processing system as your slave, or your processing system as your master and programmable logic as your slave. Next, there are some XADC also. So you'll be having a inbuilt FPGA like in the FPGA fabric itself. You'll be having a locked little converter, okay? And we'll be having some EMIOs. That is your extended multiplexed input output. First, we'll try to understand the PS part. So the PS part, we will have like if you talk about a Zinc 7000. So here you are having dual cortex ARM A9, dual cortex A9 MP core processors will be having. So apart from that, you'll be having 512 kb of L2 CAC. So there will be a Snoop control unit to maintain a coherency between these two blocks of your processors. There will be separate timing counters, interrupt controllers, dynamic memory allocations, and on-chip memory of 256 KB. And then, for if you talk about your low-speed communication interfaces, so for that we're having 2x of serial peripheral interface. You have I2C, CAN, UART, GPIOs, SDIOs, like that is for your SD card input output, your USB, and your this is for your Ethernet. So all of these are connected to a 54 clocks 1 mux, and the select line comes from your static memory controller. So based on the static memory controller's input, we are going to get the select any one of these communication interfaces for my for integrating any external peripherals that we require. So let's say if you want to interface a sensor. So in that case, let's say you have to use a SPI. So we can use those one of it for my connection with that peripheral. So now if you're talking about the EMIOs, so let's say if you are connecting multiple peripherals of like temperature sensors. So in that case, what happens? Like if you're out of your SPI memory, so in that case you can use your EMIOs, that is your extended multiplex input output. So you can program this is in your FPGA fabric. So you'll be able to program any one of those peripherals to act as a other peripheral. So I mean to say like you can use the EMIO pins that can be configured as an SPI. Okay. Moving ahead. So there will be after the Ring 7000. So if we talk about the higher end boards, so there will be ultra scale series. So that will be based on Ring 7000 itself. So the main difference that we have here is there will be multi-core processors. So here, if you talk about the 7000 series, there you are able to see only there will be APUs will be there. That is the application processing unit, and that is a dual core. Talk about the ultra scale plus, there will be application unit, processing unit that will be a quad core, and that will be based on your ARM Cortex A53 processors. Okay, and there will be separate block for your RPU, that is your real time processing unit, and that will be like this is designed to handle tasks with specific timing constraints. So it is used for applications where automation is there. Right? Now, if you talk about the GPUs, so there is a so this helps in the parallel processing capabilities and for tasks like image or video processing or any streaming applications that you perform. Apart from that, there will be separate blocks for your security, which can handle your encryption decryption tasks for a separate block for your PMUs, platform management unit. So if you see in your ultra scale boards, there will be fan, there will be some more power will be used. So for that, there will be a power management unit. Apart from that, for memory, we have DDR controllers. So will have DDR4 support, LPDDR4. Apart from that, as we know, there will be a 256 KB of on-chip memory and a separate block for your system controls, where you'll be having your watchdog timers, your interrupt controllers, your clocking wizards. All of these will be inside your system control block. And in addition to the low speed general connectivity that we have seen in the earlier architecture, like your Ethernet, CAN, UART, SPI, Quad SPI, NAND, SD cards. So apart from the general connectivity, you'll also find some high speed connectivity. So that is the DisplayPort, USB, SATA, PCI, PSTTR. Okay. So this is about the PS part. And the PL part you'll be able to see, and in addition to that, there will be some video codec unit. So these video codec unit that will be helping you to convert your S264 S264 to S265, like perform some video applications. That could be like, that is a high-speed communication protocol designed for interconnecting network components like your routers, switches, okay? And storage elements. We have block RAM, ultra RAMs, DSPs. So this was all about the architecture. So now we'll see after implementing a design, we'll see how those whatever resources that we are going to plan, how they are going to get implemented on my FPGA fabric. Okay. So as per Gaurav sir's request, so we are going to have a design on VIO. So we are going to design a 32-bit counter using a virtual input output. Okay. So as you are all aware of the early process, I'll just create a new project and we'll start. So board, as I have a ping Z2 board available with me, I'm just selecting a ping Z2. Next. Yeah. So as you know, like we can design a counter using your RTL listener. You can write an RTL code. That also you can implement, like add your VIOs and all. So, but here what we are going to do is we are going to design a counter, a 32-bit counter using a VIO, and we'll also analyze we'll be able to debug our logic using a ILA. So we'll start with this. So here I'm going to start with an. So this is my Vivado, and on the left hand side you can see we have a flow navigator. In the flow navigator, I'll go to this IP integrated block, and in this IP integrator, I'll just open this create block design option. So I hope everybody is aware of this IPI, Vivado IPI, like IP integrator and IP catalog uses. Hello. Shall we go into the PPT part of that VIO, or I mean IPI, or shall we start with the practical right away? Hello, Gaurav sir, are you there? Okay, we'll start with the practical itself. So when you open a block design window, so here you'll be able to see canvas. This is my canvas where I'll be designing my system. So here I'll be adding IPs to create my system. So first of all, I need to add a counter. So I'm going to implement a counter. So I'm going to add a binary counter here. Okay, so my counter is added. And first, so if I want to customize this block, just double click on this, and I want to have a counter of 32 bits. So I'll give my output width as 32. Okay. My increment value for the counter will be 1, x1. And this is not a loadable counter, either it is it's an up counter, yeah. Okay. You go to control if you want to set up your clear, continuous clear, or continuous set values, you can do that. So here I am just enabling a clock enable signal for this. Okay, so here you can see I have a clock signal, I have a control enable, and my output I am having a 32-bit counter, 31 down to 0. Okay, so the count mode is up, it's a 32-bit up counter. Okay for this. Next thing, what I need to do is, so if you want to add a clocking wizard, so you can directly add a clocking wizard from here. Otherwise, if you run the connection automation, the Vivado tool will automatically add clocking wizard for you, where like it will get the clocks from either you can connect the custom clocks with clocking wizard, or you can use the system clock itself. So I'll just connection automation. So this will connect both the blocks, that is my C counter and my clock. Yeah. So now you can see my binary counter. Now it is getting provided with the clock from clocking wizard. Okay. So as we were talking about your blocks in FPGAs, so there will be clock manager tiles in your FPGA fabric itself, right? So, excuse me. So there will be clock manager tiles in your 7 series FPGA. So these clock manager tiles, either it can be your MMCM or it can be a PLL. So your MMCM stands for your mixed mode clock managers, and your PLLs are your phase lock loop. So if you can see here, we have two options here: MMCM and PLL. So if we talk about just a brief introduction about MMCM and PLL, so it's a very large topic to cover. So if you talk about MMCM, it can generate like multiple output clocks with different frequencies from a single clock. So if you have this single clock, from this single clock out, we'll be able to generate a multiple clocks of different frequencies. Right? You can see here. If you can see clock out 1, 2, 3, 4, so you can be able to create multiple clocks with different clock output frequencies. Okay, so that is one advantage that we have while we are using the MMCM block. And apart from that, it also helps in your data correction, and also it supports your dynamic reconfigurations. Okay, but if you talk about the PLL, it won't support your dynamic reconfiguration, like your powerful reconfiguration. It won't be supported by PLLs. It's only supported by MMCMs. So in PLL, phase lock loop, it is also more or less same like MMCM, but it will like just it will have your helps in frequency multiplication, phase shifts, right? So that is what where it they are used. So if you talk about the boards, the interfaces here, so I'm just customizing this clock. So I want to have a clock in, so you can have multiple clocks in. So I'm having a clock in which I'll set it to system clock. Okay. So you can give a custom clock. So if you want to generate your own clock using an oscilloscope, so you can connect a microcontroller and you can give your own clocks. But here you can use a system clock, which will be a system generated clock from your FPGA board. Okay, so I'm giving system clock. Clocking option, I'm giving MMCM. Okay, I don't need any dynamic reconfiguration. I need phase alignment, frequency synthesis. Okay, and jitter optimization is there, balanced. It will be balanced. And for output clock, I'm having one clock out that will be used for all the other blocks that I'm going to use. Okay, yeah, this is the MCM settings you can do. And this is my summary. Okay, just yes. Now the next thing that I'm going to add is I need to add a VIO. So if you talk about the PingZ2 board, if I'm talking about, so in PingZ2 board we only have four LEDs where you can see the outputs. But I want to implement a 32-bit LED, a 32-bit counter. So I don't have so many input output pins where I can see analyze my input or output. So what I'll do is I'll use a VIO here. So I'll just add one VIO IP, virtual input output. So I'll just customize this. So my input probe count for this will be I'll be having only one probe. You can change it based on your users, but here I'm going to have only one probe. Okay, and the probe input that I'm having is that I'm going to give it as 32 bit. Since I'm going to connect the output of my binary counter to my virtual input output, so I'll give the input probe width as 32, and my out will be equals to 1. I'll be getting one output at a time, so my probe out will be width of 1. Okay, this is done. So as we discussed, we are going to connect the output of my binary counter to my input of my virtual input output. Okay. So now the next thing that I'm supposed to do is I need to have a ILA. I need to have one other block. So here what I'm supposed to do is here I need to add a first thing we have to do is we have to connect this output that I'm having for the virtual input output that I'm going to connect to my binary counter, the input of my binary counter. I'm doing so that I'm able to control this clock enable signal. So if we talk about the VIOs, VIOs are like you can uh, when we are going for VIOs, if you're going for VIOs, these all blocks can be like you can use it as per the like you can change the settings for this. Like if I say if I'm connecting this to my input of my clock enable, so when I'm going to run my block bitstream and when I run my hardware manager, like when I launch the project on my board, I'll be able to control this clock enable signal. So that is a feature that is being provided by the VIO. So we'll see that. We'll see how it works exactly. So for now, I'm just connecting the output of VIO to my clock enable. And the next thing I'm going to do is I'm going to add a logic analyzer. So if I want to see all the outputs, right? So for that case, you need to add a logic analyzer which will analyze your logic and you'll be able to see the output on your waveform stream. So for that, I'll add an ILA, integrated logic analyzer. Okay, this is my ILA. So if I double click on this, so as we discussed in our earlier slides, so whatever communications we are doing inside my FPGA, when we are communicating with my processing system to my FPGA fabric, so we use basically three kinds of communication. Like we use AMBA protocol, and in that we use AXI protocol for communication. So in AXI also we use either AXI Lite, AXI simple AXI, and we use AXI stream. So use AXI when you are communicating with high bandwidth. You need high bandwidth connection. You are communicating with. You have to high throughput. You use AXI Lite when you communicate inside the fabric itself. You communicate inside the processor itself. You're not communicating to any external peripheral. In that case, you use the AXI Lite. Okay. And AXI Stream is used for your any applications that you're going to perform for your video or web processing. So here I select the option as native since I'm not having any connections with my processing system. So we can have it as native. So number of probes is only one since I have only one output for my binary counter. And the sample depth you can change it according to your requirement. So I have it the samples. I just want to create 1024 samples. So I let it be 1024 itself. And the probe width that I'm going to give this probe. So this will be equal to 32 bits. That will be equal to my output of my binary counter. So I give it as 32. Okay. And I connect the output of my binary counter to this particular integrated logic analyzer. Now, one more thing, like if I want to see some outputs on my board, I also want to see the configurations on my board, some countings I want to see on my board. So in that case, what I'm going to do is I'm going to add a slice. So if you just right click on this, click on add IP, you can see there's an option called slice. So there will be XI register, stream register slice, XI register slice, or slice. So I'm just using, not using any processing system, so I'll be using the simple slice here. So by default, you will be able to see 32-bit input slice will be added to you, and the D out width you can set it according to the board configuration. Right. So this is basically this particular block is used to slice out the output. So it will take 32 bits as input and slice it out whatever bits you require as an output here. So you can just double click to minimize to customize. So the input width is 32. day input from. So I want to do it as I want to have 26 to down to 23. So this makes up to 4 bits. So I have 4 LEDs on my board. So what I do is I'm just taking the outputs from 26 down to 23. That is 4 bits output I'm taking from my board. It will take 32 bits and slice it out to 26 down to 23 and give me the 4 outputs on my LEDs. Okay. Next thing, I'll just connect this to my output of binary counter will be connected to the input of the slice register. And this pin that we have, I'll make it as external. I'm making it as external since I want to have one, I mean, like I want to control this and see the output here. So I'm making it as external. And next thing is you can connect your clocks from here. You can add these clocks to your all the other clock input that you have. Your ILA has clock, your VIO works on clock, right? So you can your binary counter is already connected. So what I'll do is I'll just simply run the connection automation, and it will automatically like connect all the blocks. Like it will connect all the clocks and all. So I just run connection automation, automate all the blocks, and click OK. So you'll be able to see external pins for my system clock and reset will be added. So these two are my system reset and system clock. Okay, and this is my output that I'm going to have. All my clocks and everything is connected now. So once you are done with your design, so you need to whenever you are going to have any block designs, so you'll be able to see inside your design sources, the sources window, inside your design sources, you'll be having dot PD file generated. So this PD file has to be converted to your HDL file, right? To go for your BitStream generation or your implementation, whatever you are doing, you need to have a top level V file or your VHD file, whatever you have. So we need to run the output products for this, and also we need to run the HDL wrapper. I need to create the wrapper for this, which will automatically create a top level .v file for this. And that top level .v file will be used to for further application, that is synthesis, running, implementation, bitstream generation, and all. Okay. So this is all about the design. So what I'll do, I just close this because if I go run all of these, like if I run the output products and if I create the wrapper and all, and I create the simulation synthesis, it will take some time. So I'll just close this. I've already made one design. So I'll just don't save. Okay. And this is the same design. So for which already the synthesis has been done. Already the bitstream has been generated. So here we can analyze our design. So first of all, what I did is inside my synthesized design, just open the synthesis design which has been synthesized. Okay. Yes. Yeah. Inside my synthesized design, so you'll be having your output ports. So what you need to do is your scalar ports will be already assigned to the system clock and system resets. Just you need to whichever port you have made external, that I made my D out port as external. So I have assigned it to the 4 LEDs here. This is a manual process which you need to do. Either you can add an XCC file directly, assigning all the 4 pins, or you can directly do a IO planning project and directly you can assign the pins using this particular pin option here. Okay, and the LV CMOS voltage and all you can see it from the XCC file that you have present in your system. I mean, in your it's available in your website for the ping board or whichever board you are using. It's available. From that, you can see the IO standards. You can check the package pin number and you can assign the pin accordingly. So now talking about the implemented design. So if I see open the implemented design here, so if I go to layout for planning project, I'll open. So now you can see here, this is my virtual representation of how my FPGA looks, like to discuss in my PPT also. So this is a virtual representation. On the sides you have your virtual input output, like you have your input outputs, all of these are there, and then here blue color mark that you see here, this is your implemented design. So whatever we have programmed, that will be implemented here. So let's see what are there, what all are there. Okay. So if you go inside this, first thing you can see here is you'll be having a BRAM. So BRAM write, that is also implemented. So that is used for being used to store your data. Okay. Next, in if you see like you have some in this block, if you see this is a CLBL Y94 slice number. So here, if you have see you can see a 6 input LED is being used, and all the flip flops are being used here. So similarly, you can check for others like what are all the resources being used. So if you drag it a little bit this side, you'll be able to see the clock manager tile as well. Let me check once again. Yeah. So if you see here, this is your clock manager tile that is being used, and as we have already selected an MMCM type, so this is my clock manager tile. Apart from that, there will be some CMT FIFOs that could be used in your design. Like if you're going for some, uh, like if there are some clock domain crossings or latency management that has to be done, that has to be taken care, then the CMT FIFOs and all that could be also used in your design. Right? And here you can see these are all your input output bands. Right? This is a G19 pin number. So whatever pin number you have used, that will be marked, another pin number will be idle. We could see we have marked, yeah. So at 16 pin, we have marked. So this pin is being used one of my as one of my outputs. Okay. And what else do we have? So we have some buffered input outputs, and all these in between, which you can see, these are all your interconnecting resources. So through this, all your slices like slice ML. So yeah. So as we discussed, like each CLB. So if you see inside this block, this each CLB, this is the block that I have. So each CLB will be having two slices, and in each of the two slices, you're having some 6 input LUTs, four number of 6 input LUTs. You'll have X7 muxes, F8 muxes, two F7 muxes, one F8 muxes here. Apart from that, you'll be having for carry look ahead and carry look ahead logic, you'll be having a carry chain here, which will consist of your muxes and your XOR operators. Okay, and then you have your D flip flops. Okay, which can be used as your either as your latches or as your flops. Okay, I hope it's clear. Apart from that, there are also some input-output logics will also be there. Like if you are going to implement some design, so if you can see there will be like I/O buffers will be added, input buffers, output buffers, and for clocks there will be clock buffers that will be added. So all of these are taken care by your I/O logic. Okay, so there will be your I/O logics that will take care of it. Mm, Yeah, so these are your IO logic or O logics will be there, I delay will be there. So like this will be used for your input buffering, or O logic will be used as your output bufferings, right? For data serializations or like decelerations. and there will be some eye delays. So these eye delays could be used for your like fine tuning. Like if you're doing for some going for some timing constraint designs, in that case you can use this eye delays will be used for your to fix your like fine tune your arrival time and all or calibrations. So now if we go to the utilization report, so you can just go to this utilization and generate a utilization report to see your design. So here if you see, we are having some like this is the complete number of LUT that you are going to have on your board. So I have 53,200 LUTs, and out of these LUTs, total number of LUTs that are being used is 1331 LUTs are being used. The registers that you're having, so slice registers will be 2355 total are being used. F7 muxes, total number of three F7 muxes are being used. Slice, if you see, total we have 13,300 slices in total, and out of that, 633 slices are being used. Now, as we discussed, we can use LUT as logic in slice L, and we can use LUTs as memory or logic in slice L. So if you see LUTs which are being used as logic are 1219, and LUTs which are used as memory as 112. Okay. So out of these slice 131 only, 1219 for your that and 112 for that. Block RAM, one block RAM will be used. Bounded input output bands. If you see six bounded input output bands are used. So six are used because we have yeah. So you can see we have four outputs 0, 1, 2, 3, 4, and we have one reset, another system clock. So for this, six bounded input bands are used. BUFG control, three clock. I mean, BUFG control are used for your clock generation, like clock distribution. So three of them are being used. So as we have connected my clock to my ILA, to my VIO, and to my counter, so three will be used. And MMCM block, one of my MMCM block is being used from my clock minded tile. So total MMCM block available are four, out of that one is being used. And the BSK logic, as we discussed about, like it can be used to hardware for hardware debugging. That or that is one of it is being used. Okay. So this is all about the design now. So if you see the working of the this counter, so we'll just open the hardware manager. First of all, I'll just switch on my board. I'll open hardware manager. Open target. Auto connect. Okay, I'll go for program device. So I'm programming both my bitstream.bit file and my debug program. That is my ILA. Program this. Okay. Yeah. So this is my ILA window. So in your ILA window, you'll be able to run your waveforms and modify, debug your designs. So this is my 32-bit counter. Here you can set up your triggers. So here if I see, if I run this now, so I'm getting 0, 0. Since if you look at a design, so that works on a clock enable. So we have already made a clock enable as 1. So we need to make a clock enable to 1. So as I discussed, there will be two separate windows, hardware ILA and your hardware BIOS. That is a virtual input output. So if I go to virtual input output, so these are my two of my uh, probes that I've added to my VIO. So one of my probe, this is my output of my binary counter, and this is my input of my binary counter. Sorry, this is the output of my VIO, and this is the input of my sorry. This is the input of my VIO, and this is the output of my VIO. So this means this is the output of my binary counter, and this is the input of my binary counter. If I think I confused you, so I'll just open design once again. Inside, uh, let's just open once. So what else I've done here is like inside this probe that that's my count enable probe that is one. So this I have made as toggle. So if you want, you can also uh, make it as active high, like it will be always be active high, or if you can make it as active low. And if you do it as a toggle button, so if you just click on this, it will start counting. Okay. So we'll first see the design, then we'll go to start. Okay. So this is my design earlier which we are seeing. So here if you see like this output that we have connected, so this is the input of my virtual input output connector. The counter's output is my input of my VIO, and this output it is the clock enabled signal of my binary counter. So that is what is here. So this is my output of my binary counter and input of my VIO, and this is the probe out from my VIO counter the clock enable signal. So I just make it toggle. Okay. So if you can see here, this will start counting one bit at a time. So here, if I now run the waveform, you'll be able to see this is running now. Okay, so I'll just stop this and I'll just see here. Yeah, so if you see, it's counting from 4, 5, 6, 7, 8, and so it counts. So if I just run it now once again, so it will be fixed at one point. So it is fixed at currently at 5D to 8DC. Yeah, so this is fixed at this. So currently in my board, so if you remember, we programmed it down 26 down to 23. So 4 bits we programmed it. So currently in my board, I'm able to see my 26 bit is high and my 24th bit is high. Okay. So these two bits are high, which means my two of my LEDs are glowing on my board. Okay. Yeah. So that is all about the VIO project. So if you have any doubts, you can just ask me. Otherwise, we can just close this session. Yeah, Gaurav sir, are you there? Hello. Hello, Gaurav sir, are you there?
Hello, hello, sir.
Ah, yes, yes.
Any doubt? No doubt, sir. Thank you so much, sir.
Okay, okay. Oh, one more thing. So before leaving this call, I just request you all to kindly fill up this feedback form. So I'm pasting it in the chat box. So sir, I just request you to get it filled by all participants that have attended these session now. So I pasted it in the chat box. You can all check it in your chat window, and please take out some time to fill this out. Okay. Okay. So can we close this call now? Hello. Can we close this call?
Sir, recording. Recording.
So one more thing here is like when you're doing this, so there will be some trigger set up here. So that when you're using ILN, a trigger will be set up by default as like if you're using the number of samples as 1024, the trigger will be set up as 512. Okay. So this here also we'll be able to see here. Yeah. So this is trigger is set up in between 512. So this you can modify as per your needs. Okay.
Yeah, shall we start?
Sorry.
Hello, hello,
Yes, yes, I'm hearing.
hello. जी सर.
Gaurav sir.
सर को बुलाएं. सर को बुलाएं. Right now, Gaurav sir is not here. He is.
Yeah, I just spoke to him. He said that he is coming in 1 to 2 minutes.
Okay, sir, please.
Okay. So by the time, I just request you all to kindly fill out the form that I've already shared with you, the chat box.
Okay. Yeah, it's my screen. Okay, sir. So yeah, this is Kumar from Coreel Technologies, and I'm the application engineer there. So we basically deal in FD Xilinx and Siemens CDA portfolio. So if you have also heard about Sandeep, who is the authorized trading partner for FD Xilinx in India.
So basically, we are working with Sandeepni. Sandeepni is a sister company. So, like if anybody is interested to go for any internship programs or if you want to learn more about FPGAs and everything, so you can anytime opt for Sandeepni programs, which are based like available on chargeable basis. So just this is about the information for the students. So we start with the session. So today's like agenda for today, as we have discussed, will be like we'll be talking about the FPGA architecture, like what are the advancements there in the 7 series architecture, what are the resources available, and how we can utilize them, and also we'll have we'll be able to virtually look at the architecture of the FPGA while we do the practical sessions also. So, talking about the practicals, we'll discuss about a small example on VIO. So, we'll see how we can design a counter using IPI, Vivado IPI. Okay. So, let's start about the 7 series FPGA. So, if we talk about the 7 series FPGA, so these things that you can see here, like the logic resources, memory multipliers, programmable interconnects, input output bands, global clock buffers, boundary state. So these things are like common to all series of FPGA. So what advancements we have seen in the latest 7 series is. So if we talk about slices, so slices are basically of two types. One is the slice L and other one will be of slice M. So slice M we can also call it as full slice. So in slice M what exactly happens is the LEDs that we have there in the slice M that can be used as a memory or either as a logic. Okay. And apart from that, it also contains your multiplexers and carry chain logic. Okay. So these are all basically used to implement your RAMs or if you try to implement your SRLs. Okay. So anything related to memories that will be able to implement using the slice. The next thing is we have slice L. Slice L is also called the logic slice. So this the LUTQs that we'll be having that will be used for your logic and not for the memory. And apart from that, it will also have your muxes and carry chain logic.
Downloading.
And other resources if you see, you have interconnect resources which are used to connect all your these are like switching routers which are used to connect all your logic blocks, your configurable logic blocks. Okay. And we have input output bands which will be there for your having an interface with the external world from the FPGA fabric to external world, or like if you're sending some signals from your external world to the FPGA fabric. And if we talk about the other resources, we have global clock buffers. So this will be your clock buff buffers will be there. That will help to distribute your clock throughout the circuit. And we'll also have a boundary scan logic that will be using for your debugging purpose, for your boundary scan testing. So these slices are not that we talked about. So as we discussed, these slices will have LUTs. Right? So if we talk about the earlier series of FPGA, you will see that there used to be a two-input LUT, then later versions used to have four-input LUTs. So now there will be six input LUTs that will be available.
Okay, so sir, are you available, sir?
Yes,
Hello.
sir. Yes. Yes, sir. I'm aware.
Yeah, yes, sir. Thank you, sir, for your valuable lessons here. Students understand I suppose, the idea behind it, that how the architecture it works, FPGA architecture, isn't it? So I suppose, sir, if the student have any queries there, is there any query? Okay, so sir, now we have the hands-on session. So sir, thank you again for your
Okay,
valuable.
okay. Thank you, sir. Thank you very much. Sir, one more thing. I just request, like I have shared my feedback form on the this chat box. I request you to kindly get it filled by all the participants who have attended this session.
Oh, okay, sir. I will share it in the what is called that email in the group, and then uh, I request to all the participants to please fill it.
Okay, sir. And also, I'm pasting my email ID here. So if anybody has any doubts, they can just mail me on this email ID.
Okay, okay, sir.
Okay, thank you, sir.
Okay, thank you, sir.